This is Ms. Graber, and I will be taking you through the review for test on transformations in symmetry. You will see as you're going along that the numbers don't necessarily match up with all the questions, so it'll be an interesting adventure for you to follow along and find which question pertains to which one. As we begin with angles of polygons, there are three facts that we need to remember. First of all, that one, the sum of the interior angles is equal to the number of sides minus 2 times 180 degrees. As we said, n equals the number of sides of the polygon. We said in class when we break up a polygon, it can be broken up into a number of triangles, and so each triangle is worth 180 degrees. The number of triangles in a polygon is always the number of sides minus 2. So that is fact number 1. Fact number 2 that we need to remember is the sum of all exterior angles is always, no exceptions, always 360 degrees. Thirdly, third fact is that if you have one interior and one exterior angle, their sum will always be 180 degrees. They are always supplementary. So here's an example. If I have an interior angle of 120, that means the exterior angle is going to be 60 degrees. Let's get started then. For number 1, we want to find the indicated angle measure. For part A, what is the sum of the interior angle? So we want to be careful as to what the question's asking. Of a nonagon. So second thing I need to know is, or first thing is that I need to know the number of sides of a nonagon. Well, a nonagon has 9 sides. If you're not sure about your side numbers, you need to study those. So the sum is what we're looking for. So this is what we're looking for, fact number 1. So we're going to plug in the sum is equal to n minus 2 times 180 degrees, which gives us 7 triangles times 180, or 1260 degrees total. Number 2, what is the sum of the interior angles of a quadrilateral? Once again, we know that n for a quadrilateral is equal to 4. So the sum of the interior angles is equal to 4 minus 2 times 180. Equals 360 degrees. Now, most of us will probably know how to calculate this without having to calculate it. We just know it from previous knowledge of parallelograms, quadrilaterals, and the such. Part C. What is the sum of the keyword here, exterior angles of a dodecagon? Okay, we got a little lucky break here because it doesn't matter necessarily what the number of sides is in this case when we're asking about the exterior angle, because we're looking at fact number 2 in this case. Fact number 2, where it says that the sum of the exterior angles of any polygon is always 360 degrees. No calculation needed here. We just need to know that fact. Part D says, what is the sum of the exterior angles of a 23gon? Once again, I don't even need to go to C. This is really insignificant, the number of sides, because, again, fact number 2 is saying that the sum of all exterior angles is 360 degrees. E, what is the measure of one interior angle of an octagon? Well, if we know that all the sum of the exterior angles is 360, okay, and we know we can figure out one exterior angle by dividing by the number of sides. So in this case, we have ourselves an octagon, and it will be 8. So if I take 360, divide that by 8, that will give me one exterior angle. And one exterior angle of an octagon is 45 degrees. So this is one exterior angle. Now that I know that this one exterior angle, I can go to fact 3. So this is sort of a combination of fact 2 and 3, saying that Now that I have one exterior, I can say that 45 plus my one interior, I'm going to say I for interior, is equal to 300. I kid. My mistake, I is equal to 180 degrees. So I can just take and subtract 180 from 45, and I get one interior angle equal to 135 degrees. So everything still in part E is revolving around the exterior angle. So I used fact 2 and fact 3. I found the exterior first. Once I found the exterior, I found the interior by subtracting by 180. F. I'm going to follow the same process here. What is the measure of one interior angle of a 14-gon? So the first thing I'm going to do is that I'm going to find one exterior angle. Keep in mind that this only works if this is a regular polygon. Regular meaning that all sides are congruent. All sides congruent and all angles are congruent. So going back to part F, I'm going to first find one exterior angle. Since I know, again, the sum of one exterior angle is going to be the sum of all exterior angles is 360 degrees. If I take and I divide that by 14, the number of sides, each exterior, is going to be 25.7 degrees. Now, you have to be careful. Again, our question is asking us for the interior. So the second step I need to do is using fact 3 is take 180 minus 25.7 degrees, which will leave me with 154.3 degrees for that answer there. Okay, I'm going to go back and circle these answers very quickly, just so that we know what the final answer is going to be. Here we go. Part G. We want to know what is the measure of one exterior angle of a decagon. So again, you see how we've bolded these just to make sure that you're paying attention. Don't expect this to necessarily happen on the test or on the SOL test. Angle of a decagon. A decagon has 10 sides, so 10 is that. So now I'm just going to use fact number 2, where we say the sum of the exterior angles is equal to 360 degrees. If I take that and I divide that by the number of sides, that will give me one exterior angle, which is all that I need. So my answer is going to be 36 degrees for part G. Lastly, part H, what is the measure of one exterior angle of an 11-gon? So I'm going to follow the same process. Once again, I have 360 degrees divided by the number of sides, which is n, which is 11 in this case, and that's going to give me one exterior angle of 32.7 degrees. So as long as you have the three facts underneath your belt, then you should be able to handle all of these. Now, each teacher of us are teaching it a little bit differently, but again, these three facts remain. Now, taking a look at the rest of the first page, we find the number of sides of a regular polygon. So again, we just discussed what a regular polygon means. It means all sides are congruent and angles are congruent. For part A, we want to find the measure of one exterior angle is 24. So here, what is the question asking? It's asking us for the number of sides n. So what am I going to do? Well, I had been taking and dividing 360 by the number of sides to get an exterior angle. If I take the converse of that statement, then that means I can also divide 360 divided by one exterior angle to equal the number of sides. In this case, that's what I'm going to do. So I'm going to take 360 divided by 24 for the one each angle, and that's going to give me 15 sides. So I have a 15-gon for part A. Part B, the measure of one interior angle is 156 degrees. So this time they give me an interior angle. Notice on part A they give me an exterior. So the first thing I need to do is find one exterior angle. How do I do that? Glad you asked. I'm going to take 180, subtract that by 156, so that's the supplement. 180 minus 156 gives me 24. 24 degrees, so this is for one exterior angle. Now, you might see this looks familiar to part A. So if I have, but keep in mind that this is one exterior angle. So I'm still following this piece here, but it's still calculating and dividing it into 360. So in this case, it's going to be 15 sides. So wait a second, we have A and B as being the same answer. Yes. So what this is showing you is that these are two different ways of asking the same question. So keep that in mind, how different ways, how they might ask the same question. Part 3, we want to solve for x. First thing I need to do is I need to figure out what is the sum of the angles of the interior. Well, I take a look at the number of sides here, and that means I'm going to have 6 sides. 1, 2, 3, 4, 5, and 6. So if I plug it in for the sum, that's going to give me 6 minus 2 times 180, which equals 4 times 180, which is going to give me 720 degrees. Now, some of you may know that by memory and may not need to use that calculation, and that's absolutely fine. Once I do this, I need to take and add up all the given angles that I have so far. Because whatever these add up to, I'm going to take and subtract that from 720 in order to find x. Well, if I take and I add up all of these angles here, it gives me 610 degrees. So 610 degrees for that sum. Total is 720 degrees. I'm going to subtract the two, and that's going to leave me with 110 degrees for x. Number 4, find the sum of the measures of the interior angles of a quadrilateral. Hopefully this is not one that we have to spend too much time on. We've done quadrilaterals plenty throughout the year, and so we should know that the angles is 360 degrees. If you don't, 4 minus 2 times 180 is going to give us 360. As we now look at number 5, the measure of each interior angle of a regular hexagon is, so here, what's it asking for? It's asking for an interior angle, and it's of a regular hexagon. So that means we've got n is equal to 6. Keep in mind, to find the interior angle, I first find the exterior angle, because it's easier to find the exterior angle of a regular polygon. How do I do that? I take 360 divided by 6, and that gives me 60 degrees for one exterior polygon. So each exterior angle is equal to 60 degrees. If I remember fact number 3, they are supplementary, so I will take 180 minus 60 to give me 120 for one interior angle. Notice on this multiple choice, they will give you both choices. So you have to be extra careful in how you answer. See, I did that on purpose just to make sure that you're paying attention so that we have our answer as being 120. Number 6, the measure of each exterior angle of a regular octagon is. So here, this is really just a one-stepper because we just take and divide that into 360. Octagon has 8 sides, 360 divided by 8, and that's going to give us 45 degrees. We don't need to do anything more than that because it's the exterior angle. Finally, number 7, the number of sides of a regular polygon where each interior angle is 144. So here we're trying to find n, the number of sides. Regular polygon, and you have each interior angle, careful, is going to be 144 degrees. So the first thing I want to do is that I want to subtract 144 from 180 in order to get an exterior angle. So I have an interior, I want the exterior angle. If I subtract 144 from 180, that's going to give me 36 degrees. At this point, I'm then going to take 360 divided by one exterior angle, and that will give me 10 sides, not degrees, but sides. So I will have 10 sides in this case. So we have ourselves a decagon. Again, being able to distinguish between number of sides and names is going to be always important. On the second page, we have a little bit of application here. So we want to find with the center, what is the value of x? So sometimes on the SOL test, they will give us very fancy figures, but it's really the calculation is pretty simple. So we need to identify where x is. Well, x is on the exterior of this polygon. So I am looking for an exterior angle. Again, I want to keep in mind that the sum of exterior angles is 360 degrees. Now I need to figure out how many sides do I have here. 1, 2, 3, 4, 5, 6 sides for this. So notice that the circle really has nothing to do with the problem. It's just there as a visual. So sometimes you're going to have, as I said before, these fancy figures, and it looks very intimidating. However, it's not difficult at all. Just take a second and see what information you need and what you know and work the problem there. So now 360 divided by the number of sides, n, is going to give me one exterior angle, which will give me 60 degrees. Okay. Again, at some point, because this class is full of patterns, some of us will know just by practice, remembering that the exterior angle of a hexagon is 60 degrees and can do that without calculation. Number 9, if the interior angle of a regular polygon is 175 degrees, that's interior, how many sides, n, does the polygon have? So remember, the first thing, most things are revolving around the exterior angle. We use the exterior angle to get to the interior, to the number of sides. So I'm first going to find my exterior angle by subtracting 180 minus 175. So we see that one exterior angle is going to give us 5 degrees. And that seems that that's very small. Well, yeah, it is pretty small, which means when I take 360 divided by 5 degrees, that will give me my number of sides as being 72. So 72 gon is what we're looking at here. For number 10, as we scroll down just a little bit. Again, here's another fancy question that's asking a pretty simple concept. So if I want to find a quilt design piece is made up of 8 congruent parallelograms. So what is the measure of angle 1? So we have angle 1 right here. Well, in order to figure this out, this is what we call a tessellation, where we have a repeated pattern and there are no spaces. There's no gaps in between the adjacent polygons. So I'm going to look, if I look around this center angle right there, all of these points come to surround one point. And if I know that they all come around one point, which is going to add up to equal 360 degrees. So if I want to find one of those, because there are 8, these are all going to be congruent because it says so in this, I'm going to take 360 divided by 8. So if I take 360 divided by 8, that will give me one interior angle as one of those angles as being 45 degrees. So each of these interior angles here are 45 degrees. So notice how it doesn't tell you to find these angles first. It's an implication that you need to find this first. Second fact that I need to know is that it's a parallelogram. So right, parallelograms, we have interior angles. Consecutive interior angles are supplementary. So that means angle 1 plus 45 will equal 180 degrees. So lastly, what am I going to do? I'm going to subtract 45 from 81, and that will give me 135 degrees for J. Here, number 11, label each statement true or false. All triangles tessellate. Let's think about what it means by tessellate. So we're talking about in order for it to tessellate, everything has to come to one point. So if you have something, if you're tessellating a triangle of any sort, yes, please don't be intimidated by my amazing drawings, you see that there will be no gaps. And coming around this point, as we stated in the previous question, it always comes around 360 degrees. So if we have an object where its angles will always be able to add up to 360 degrees, then yes, it will tessellate. So in this case, all triangles will tessellate because their interior angle sum is equal to 180 degrees. So that will be true because I have a sum that is a multiple of, or a factor of 360 degrees. The same fact will be true is that all quadrilaterals tessellate. Now this is if they are on their own. Say, like for example, looking at this example here, these were all congruent parallelograms. So these will tessellate because of that. Again, their sum is 360 degrees. Therefore, it will also be able to tessellate if it's the same quadrilateral tessellating. Thirdly, if we look at part C, all hexagons tessellate. Well, if we look at their interior angles, each one is 120 degrees for each interior angle. So that means that a hexagon, this is only the case if it is a regular hexagon. If it's not regular, then it's not going to be true. So we're going to say false. The reasoning is that only if it is regular will it tessellate and have a factor of 360 degrees. So only if it is regular. Because the sum, once more, of a hexagon is 720 degrees. So it has to be specifically regular in order for that to work. Taking a look at number 12, we want to explain why a regular hexagon will tessellate, but a regular heptagon will not. And as we said, for it to tessellate, its interior angle must be a factor for it to tessellate. The interior angle must be a factor of 360 degrees. In the case of a regular hexagon, which has 6 sides, 720 divided by 6 means that each interior angle will be 120 degrees when I take and I subtract that from that. So yes, that will have a factor of 100, have a factor of 360. However, if I take a heptagon has a sum of 900 degrees. If I take that and divide that by the number, let me back up just a second. So if I want to find one exterior angle of a heptagon, I would take 360 divided by 7, which is going to give me 51.4 degrees. And then the interior angle would be that divided by, or subtracted from 180, which is going to give me 128.6 degrees. So therefore, this is not a factor of 360, and therefore will not tessellate. Okay, taking a look at number 13, I went ahead and listed what each individual interior angle would equal of these regular polygons. Remember, all of these need to be a factor. In order for it to tessellate, the interior angle needs to be a factor of 360 degrees. So if I were to take this number and divide it into 360, if it goes into a wholly, then it will work. So that means 360 divided by 120 will work. So this is a hexagon. Regular hexagons will tessellate. B, 108 does not go wholly into 360, neither does C. Lastly, as we said before, D, the triangle, because its entire sum is 180 degrees, all triangles will tessellate. I just went ahead for number 14 and did a quick tessellation to show an example how a tessellation is just going to be a figure with no gaps, and they all surround one point at 360 degrees. That's essentially what we're looking for there. If we take a look at 15, this one says what's the value of x in the tessellation below. So as we've talked about, remember it all comes around 1 point so that it's 360 degrees. So that means I'm going to take x plus 20 plus 3x minus 10 plus 3x minus 10, again, plus 2x equals 360 degrees. Now you see the end product combined like terms. We will have 9x is equal to 360 degrees. So there we would take and divide 9 by both sides, and we end up with x is equal to 40. Okay. Just wanted to mention at any point where you would need to pause during the video, please feel free, or rewind if you have missed something. Looking at number 16, sometimes it would be easier just to say what does tessellate rather than what doesn't. So if we take a look over on the column here, we see what are the polygons that will tessellate. So we already established that all triangles will tessellate because their sum is 180. All quads will because their sum is 360. And regular hexagons, keep in mind it have to be regular because their interior angle is 120 degrees. So therefore, all quads and all triangles will tessellate, but the octagon will not because it is not one of those listed. You look at 17. It's very similar, pretty much asking the same question, which will tessellate the plane individually. So keep in mind all of those that are triangles and quads. So parallelograms, isosceles traps, squares, regular pentagon is not in that category, and then a regular hexagon for that. Taking a look at number 18, we want to see which two figures together, so this is different than individually, will tessellate the plane. So we're still looking for angles that will add up to 180 degrees. We found the pentagon is 108, octagon is 135. This, an isosceles right triangle, we are assuming that it is a right triangle, which we shouldn't usually do, but we will in this one case. We have then a couple quadrilaterals and another triangle. The only ones that we know definitely will tessellate together will be the octagon and the isosceles right triangle, because if I take a look at their two interior angles, 135 plus 45 will equal 180 degrees. And so then that is a factor of 180. So while an octagon does not tessellate on its own, not individually, it will tessellate with something else that has an angle that will form a factor of 360 degrees. Number 19, we're trying to define an isomorphic transformation. So isomorphic is meaning that it preserves shape and size. So the ones out of our 4 transformations, we have translations, rotations, and reflections will be isomorphic transformations. It does not include dilations because dilations change size. There we go. Okay, at this point we're getting into some transformations, and you may notice that the numbering is changing a tad, but you should have this in your packets somewhere. If you don't, then just watch along. So for number 20, you want to fully describe. So here we have a huge table here to kind of help give us a visual of potentially what might look like on an SOL test as far as fill in the blanks. Well, we only need to use one of these, and looking at this we need to figure out which one of these that we're actually going to use. So if I take a look, now it's important for me to know that what they don't have labeled here are the letters, because if they had the letters labeled, that might change my answer. So I am assuming that this is A prime, B prime, C prime, and D prime. This actually isn't a great example. So keep in mind that this is going to be a reflection because it is a mirror image. This C is one above, C prime is going to be one below. So one below is going to be then that's reflected across. So if we're looking at a reflection, it's going to be across the line. Now look at the notation here. The line is going to be y equals 0, which is the same as the x-axis. Knowing that those two things are the same, they might ask you for either question. Okay? Since this is a little bit tricky and we didn't have the labels, the points labeled, if perchance I had and put these as being B prime, A prime, D prime, and C prime. If I had my points labeled that way, this case, it would be a rotation of 180 degrees. And remember, it doesn't matter whether it's clockwise or counterclockwise when it comes to an 80 degrees. And that would be always about the point 0, of the origin. So let's take a look at the next one. So here we want to see, is it a mirror image? Is it being turned? Is it being flipped? What's happening? And so if I find a midpoint, so if I look at this, the line, I want this to be the midpoint between two corresponding points. So what that's going to do is if there is a midpoint between that, then it's going to be a line of reflection. So here we're going to have a line of reflection, and this one, as we talked about, if it's vertical, that means it's going to have an undefined slope and it's going to have an x equation. And so it would be at -1, so x is equal to -1 because every value for that is going to be x. And what you don't see below is that the translations is down here. It doesn't fit on the screen, but know that that's a possible option. So here we have this question where it is multiple transformations occurring at once or in separate things. You can either use the graph as a visual, or you can look at a pattern. And a pattern is if you recognize certain ones are pretty easily recognizable. It is completely up to you depending on what kind of learner you are. So for part A, we have a reflection over the x-axis. So we have x-axis right here, which means it's just going to be flipping from quadrant 1 into quadrant 4. If I look at the pattern here, it means that the x values remain the same, but the y value becomes opposite. So if that's the case here, I'm just taking the originals and these are all going to be the opposite of what they were originally. Here's a look at part B for the 180 degrees clockwise rotation about the point 0, 0. So if we look at the pattern here, the pattern of rotating 180 degrees is that it will be the opposite of the x value and of the y value. If you think about it, looking over at the graph, you see that they switch to the opposite when you're rotating at 180 degrees. What once was in the first quadrant now is going to be in the third quadrant. We'll wait for the smartboard to catch up. Here we go to the third quadrant, which is at negative, negative. 1 is at positive, positive. So if you just know and see that the signs are just going to be the opposite of whatever they originally were. For part C, we're looking at a translation that's following this particular rule. So we have been using it written out. You may see it in this notation, but in words it's saying this means 2 left and then 1 unit up. So you can see how we have our transformation occurring here. So it's the same orientation, just a different location. If we take a look at part D with the dilation, that's centered at 0, 0 with the dilation factor of 3. That means if it's a factor of 3, if it's greater than 1 means it's going to be larger. Scale factor is greater than 1. So what am I going to do? It's too much to graph this on the graph because I don't really want to have points 15, 27 that I have to graph. But I can just take and multiply each coordinate by the scale factor. So for example, I took A and I multiplied it times 5 times 3 to get 15 and 3 times 9 to get 27. I'm going to do the same thing for each of the 3. If we take a look at the next one, we're given these vertices of A is negative 3, 5, B is 8, 10, C is negative 10, negative 4. And then we have our image coordinates, our transform coordinates. And what we want to do is that we want to compare and see how they differ. We can certainly use a graph and kind of give us a visual, or again, if we see the patterns, we can use that as well. So if I take a look here and I do A, which is approximately at negative 3, 5, figure not drawn to scale, and then I take a look at A prime, which is going to be negative 3, negative 5, I see that it is flipped from top in the second quadrant to the third quadrant. And I notice if I look at the coordinates that it's the opposite of y. I want to check and make sure that it's the same pattern though for b. So if I take a look at b and b prime, yes, I see that yes, it is the opposite of y. So as we discussed before, it means it's going to be a reflection across the axis. So I'm looking at a reflection and it's going to be across the line, as we said before, y equals 0 or the x-axis. So let's take a look at this next one. Again, we have vertices A, B, and C, and then the transformed coordinates as well. So again, we're looking for a pattern. That's what this whole thing is. You may use graph paper, but if you don't have it, you can look for the pattern as well. Now, if I'm taking a look at what happens with part A, it goes from negative 3, 5 to A prime, which is at negative 4, 2. Now, if I look at this, I'm looking at a reflection or a rotation. I'm going to be looking for numbers that are the same but having different signs. Since I don't see this here, I see that there is not a difference of just saying going from, say, a positive 3 to a negative 3. It goes from negative 3 to negative 4. I might want to be thinking of a translation or a dilation. But even a dilation means that it would have to be a scale factor, and it's not consistent scale factor from negative 3 to negative 4 and 5 to 2. So I want to see what have I done. Well, I have gone from negative 3 to 4, which means I have subtracted 1, and then from 5 to 2, I have gone down 3. Now, to make certain that sure, I need to check it against the other points as well. And I'm going to do 2 points, but it's always most helpful if you use all 3 points. So if I'm going from 8 to 7, what am I doing? I am subtracting the x value by 1. And to go from 10 to 7, I am subtracting the y value by 3. So if I take a look, I see that yes, this is the same as the first one. And if I checked it against part C, I should find the same thing. So depending on how it's written, you can write it as this notation, or you can write it out saying you're going to shift 1 unit left and 1 unit, 3 units down. So you might see it as notation. You might see it as written out. Just be aware that you might see it either way for that. And since I'm just writing it up here, since the table doesn't fit fully on the screen. So as we take a look at this next one, we have A, B, and C, and again, our transform figures. Now, as I'm looking and I'm comparing, I want to notice a few things that I notice from A prime, from A at negative 3, 5 to A prime, I'm seeing a switch of my X and Y values. If that is occurring, that should be a clue that it's going to be a rotation of 90 degrees. Now, we need to take a little bit step further to figure out whether it's going to be counterclockwise or clockwise. So if I take and I make myself a little bit of a makeshift graph just to figure out where I'm headed, if I take a look at A is in the second quadrant, which is a positive negative notation. And when it's transformed to A, it becomes a positive positive. So I know it's going to be in the next quadrant. Now the question is, am I going clockwise or am I going counterclockwise? Well, in this case, it is going clockwise. So I'm looking at a clockwise rotation. I want to confirm it with part B. B is in quadrant 1, which is positive, positive. And then after it's transformed, it's at 10, negative 8, which is in quadrant 2. So if I'm taking and I'm going from quadrant 1 to quadrant 2, again, that is again a clockwise rotation. So I'm going to say that I have a rotation here of 90 degrees, and it's going to be a clockwise, and we're always going to be doing it about the point 0, 0. Once again, you can always make a graph and physically turn the paper so that you can see where the new coordinates would lie. But again, you can use patterns as well. As we take a look at this next one, again, you're noticing that we are using the same 3 vertices for each of the pre-images, and then transforming it to the different images. So if we take a look at this one, and I'm using a comparison of the pre-image to the image, and I see that here there's no switching. There's really no sign changes. The signs are remaining the same. It's not a consistent being added and subtracted, but it is a factor less. And if I see this and I want to compare and do the same thing again for part B, from 8 to 10, I'm noticing, okay, the numbers are getting smaller and they're being divided by 2. Well, divided by 2 is the same as multiplying by 1/2. And when we're talking about scale factor, it is always within the form of multiplication. So it would be saying multiply by 1/2. So that means the scale factor is 1/2. And again, it's getting smaller, meaning that the scale factor should be less than 1. And then we want to see if this is the case. So 3 times, negative 3 times 1/2 is going to give me negative 1.5. Same thing, 5 to negative to 2.5 is 1/2. 8 to 4 is 1/2. 10 to 5 is 1/2. And again, if I did the same thing with C and C prime, I would find the same thing. So I'm having a dilation centered around the origin with a factor of 1/2. We have on the next one, a figure is translated 5 right and then down 3. If it's translated again, right 4 and down 8, we want to say what single transformation describes the movement from the original figure to the final figure. So I've written this out in notation form as to what's occurring. Well, we have ourselves 2 translations, which means if we put 2 translations together, we're going to end up with a 1 translation. So I'm just going to take easily the sum of how many times that we're moving right. Now you want to take into mind direction. So these are both moving right. So that means I'm going to end up moving right 9 spaces when I take the x plus 4 and the x plus 5. And then I will be going down, again, because I'm going down 3 and then down 8. And I'm going to take the sum, and that would mean I would be going down 11 for that y value.